Okay, so in this video, we're going to be going over a whole bunch of convolution examples. Okay, they're going to start off simple, and then they're going to get into more complicated examples as we go on. Let me just remind you what the definition of the convolution is. So f of t convolved with g of t, we use this asterisk symbol to denote convolution. It gives you another function of t, and that function of t is given by this integral. Okay, so we have f of tau, g of t minus tau, d tau. Okay, so you can see this is a function of t because t appears right there, and the integral is d tau. So when I perform this integral, all the taus go away, and I'll just be left with a t. So if I called this maybe some function y of t, that argument t in the convolution appears right there. That's the only place. So that argument t just controls the shift in time of this function g, and we'll see more on that later. Okay, so this is the convolution. And another form of this convolution integral is just we can flip these arguments t and tau and t minus tau. It doesn't matter whether f or g gets tau or t minus tau. Okay, you get the same thing, and you can show that just with a change of variables. Okay, so you can try that on your own. Both these integrals give you the same thing, but I tend to like to put the more complicated argument, t minus tau, with maybe the simpler function. So if g is somehow sort of, I perceive it to be a simpler function than f, I'll put the t minus tau argument with g, and I'll put the simple argument tau with maybe the more complicated function f. But either way, you'll get the same answer, so it doesn't really matter, just a little tip. So this first example is really important for us. X of t convolved with delta of t. What happens when you convolve x of t with the delta function? Well, let's do the integral. So we have x of tau, delta of t minus tau, d tau, just plugging in for right there. Okay. And now I have the integral of a function, x of tau, times a shifted delta. So we know what happens. What we get out is this function evaluated wherever the delta function is located. The delta function is located, okay, at whatever value makes this delta function argument equal 0. And you have to notice in this convolution integral, tau is the variable. T is a constant in this integral. Tau is the thing that's changing. Okay, so what I'm asking for is what value of the variable tau do I need to make this argument 0? Because that will tell me where this delta function is located. And clearly you can see that that's when tau equals t. And so what I get out of this is just x of tau evaluated at the tau value that makes this argument 0. In other words, the place where that delta function is located, and it is x of t. Okay? Because this delta function, if I were to plot this in terms of the variable tau, which is what the variable is, right? And let's say t is right here. Okay, then delta of t minus tau, I know it's located at the tau value, just to say it one more time, where this argument is 0, right? Because delta of any variable x is just located right there at 0. So delta of x is located where the argument is 0. This argument 0 when tau equals t. So that's where the delta function would be. And so I plug that value of tau into x of tau, and I get x of t. Okay, so it's just using the delta function properties we went over before. And so what does this tell us? This tells us a cool fact that delta of t actually acts as an identity element for convolution. So, you know, for addition, an identity element is 0. You add 0 to anything, you get back that same thing. For multiplication, identity element is 1. Multiply any number by 1, you get back the same thing. The operation of convolution, the identity element is delta of t. You convolve anything with delta of t, you get back the same thing, x of t. All right, so the next natural thing to do is what happens when you convolve with a shifted delta. Well, let's do the integral. So we're going to do x of tau. And actually, since I think this function is a little more complicated, plugging in for the argument, I'm actually going to do x of t minus tau. So I'll put t minus tau with the simpler function. And I'm left with delta. So I'm kind of using this formulation. Delta, where I just plug in tau for t. delta tau minus T naught, d tau. And again, this delta function, where is it located? What value of tau makes the argument 0? Well, T0, right? T naught. If I plug in T naught for tau, this argument 0, so that's where the delta function's located. And so now I just have to evaluate this first function, x, plugging in for that value of tau, right? We saw this for the delta function properties, the integral of a function times the shifted delta. Okay, and so I just get x of t minus T naught. Okay, so when we convolve with a shifted delta, it ends up just shifting our original function. So that's pretty useful too. So convolving x of t with a shifted delta function, delta of t minus T naught, what does it do? It shifts x of t by T naught to produce x of t minus T. Okay, so that's really useful too. We'll be using this all the time in this class. So convolving with delta functions is actually pretty simple. You just get a time shift. All right, so let's do an example where we're going to use this. What happens if I have some function f and I multiply it by a cosine function? Okay, and what happens when I want to take the Fourier transform of that function? How does multiplying by cosine affect the Fourier transform of f? Okay, so f of t as Fourier transform f of omega. What's the Fourier transform of f of t convolved with cosine of omega t? Well, how can we do this Fourier transform? Well, we saw a property that's helpful, the multiplication property. We saw that in a previous video. And that tells me that multiplication in time is 1 over 2 pi times convolution in frequency. The convolution of this Fourier transform and the other Fourier transform of cosine. Okay, let's expand this. So we have 1 over 2 pi times f of omega convolved with what is the Fourier transform of cosine? Well, we saw that in another video too. It's pi times delta of omega minus that frequency plus delta of omega plus that frequency. Okay. And now, what am I going to do? I'm going to take f of omega and convolve it with this other signal. Okay, and I am going to use one property that we're going to see in the next video. Okay, but you can take my word on it for now, just because I want to get to the convolution part. If I have f of omega convolved with a sum of two functions, what I get is just f of omega convolved with each of them added up. So in other words, convolution is distributive. I get f of omega convolved with that function plus f of omega convolved with that one. Okay, so take my word on that for now. We'll see that in the next video. But so what do I get? Well, this pi constants can just come out of convolution. That's another property. Pretty simple to see from the integral, right? If I just had a constant there, I could just bring it outside the integral. Okay, so constants can be brought out of convolution. So I get pi divided by 2 pi, which is 1/2. And then what I'm left with, I'll just write it down. This is the distributive property we'll see in the next video. We'll just use it for now. Okay, but at least it's sort of what you would like to see based on sort of how multiplication will work. Convolution is not multiplication, but multiplication is also distributive. Okay, so this is a nice property for convolution to have. Okay, and now we can use what we just showed up here. Because we have a convolution, it's in frequency this time, but that doesn't matter. F of omega convolved with delta of omega minus omega naught. That just gives me f of omega minus omega naught. This is what I wanted to do this example to show. F of omega convolved with that shifted delta, no problem. F of omega plus omega naught. Okay, so what happens when I multiply by a cosine? Well, I actually get two shifted copies of my Fourier transform f of omega, and they're both multiplied by 1/2. Okay, and we'll come back to this when we get to the AM radio application. This is going to be really important for us. Okay, so that's a good example too. All right, now let's try and apply that to a more specific set of functions. Let's find the Fourier transform of Sinc of 2t times cosine of 3t. Okay, so you can see that this is the same setup we have up here. It's a function times a cosine. And I'll just make a note here in case you forgot. We showed that the Fourier transform of Sinc of omega naught t is pi over omega naught times rect of omega over 2 omega naught. We saw that in the previous video. So we're going to use that Fourier transform pair now. So sinc of 2t is what? Well, it's pi over 2 times rect of omega over 4, right? 2 times 2 is 4. Why do I care about that? Well, I care because sinc of 2t is playing the role of my f of t in this example. And so I need to find f of omega so that I can create the Fourier transform of sinc of 2t times cosine of 3t. Okay, so what does that mean? That means that sinc of 2t times cosine of 3t using the property above has as its Fourier transform 1/2 times this Fourier transform f of omega, but shifted by 3. So plug in omega minus 3, right? Because omega naught here is 3. So I'm going to get pi over 2 rect of omega minus 3 over 4, just shifting by 3, just applying the shift that we derived in the previous example, plus pi over 2 rect of omega plus 3 now, right? Just shift by plus 3. Okay, and let me just clean this up real quick. So we get pi over 2 in both of these terms, I can factor out. So we're going to get pi over 4, and then I'm left with rect of omega minus 3 over 4 plus rect of omega plus 3 over 4. Okay, so that is the Fourier transform of this function. All right, and I can just plot that real quick. So rect of omega minus 3 plus 4, that's just a rect of omega over 4 shifted to the right by 3. Maybe I'll just draw what rect of omega over 4 is real quick. Remember, the rect function looks like this, and the two sides come down at whatever omega values I need to make the argument plus or minus 1/2. That was our definition of the rect function. So clearly here it's negative 2 to 2. Okay, and so if I shift that to the right by 3, now it's going to be centered at 3. It's going to go to the left by 2, to the right by 2. And this one's the same thing, just shifted to the left by 3. It's going to go to the right by 2 and to the left by 2. And the height of both of them is just pi over 4. Okay, so that's what that Fourier transform looks like, of sinc of 2t times cosine of 3t. All right, now I'm going to do a more general example to try and explain more about what the convolution is really doing. Okay, we've seen some examples now, but what's really happening? And to do so, let me just kind of draw an arbitrary x of t function. Okay. And let's say I want to convolve that with this function. I'm going to call it h of t because you could imagine this would be an impulse response to an LTI system because we know the output from an LTI system is the input convolved with the impulse response. Okay, so that's a main place where this concept comes up in ECE 45. Okay, so I have these two functions, and now down here, because I'm going to want to draw more things up there, down here, I'm actually going to write what the convolution is so that we can try and actually see what happens visually. The convolution is going to be x of tau, h of t minus tau, d tau. Okay, and we'll take that function now and try and break it down piece by piece. All right, so x of tau, how can I get my hands on that function? Well, that's pretty easy. I just take x of t up here and change the variable to tau. Okay, h of t minus tau, how can we understand what that function's doing? Well, I like to do it in 2 steps. This is what most people do. Okay, and that's called a flip and a shift. All right, so the first thing we're going to do is we're going to flip the function and put the tau variable in there, because remember, d tau, tau is the variable for my integral. And what does h of negative tau look like? That's pretty easy. That's just h of t, but flipped across the vertical axis. Okay, and so I get something that looks like this. So it goes down to negative 10, starts at 0, there's height 1/10. And the axis I've changed to tau. So now from this, how can I write h of t minus tau? Okay, how can I write that? Let's think about it. So it's a little confusing because we have different arguments and negations. So what I'm going to do is a trick I like to use. I like to call this h of tau function something else, or this h of negative tau function, sorry, something else, h hat of tau. And then let's look at what happens when I take that function and shift it to the right by t. So I'm taking this function, I gave it a new name just to make it easier so I don't have to worry about that negative sign. This function, gave it a new name, and now I'm going to shift that function to the right by t. And let's see what we get. Well, now I'm just going to plug that whole argument in for tau. So I get h of negative tau minus t, which is h of negative tau plus t, which is h of t minus tau. Sure enough, that's what I wanted, h of t minus tau. So what this tells me is that to get h of t minus tau, if you give me some t value, I don't know, say like right there, how do I get h of t minus tau? I just take h of negative tau and I shift it to the right by t. So it's going to look like this. Okay, so that's t, and then this point on the left side is 10 units to the left of the right side. This rectangle is width 10, so down here must be t minus 10. Okay, and so this is what we call the flip and shift method. And you'll hear this a lot when people talk about convolution. You flip the function, h of t, you get h of negative tau, and then you shift it so that right here, I call this sometimes the t position, because if you notice, h of negative tau is really h of 0 minus tau. So it's sort of like I plugged in 0 for t. So this is the t position in this drawing. But then when we shift it to get h of t minus tau, it's pretty easy. We just take that t position, that 0 point, and move it left or right so that it's situated on t. Maybe t here is 3, for instance. Okay. All right, so that's how we get our hands on these two functions, h of tau and, x of tau and h of t minus tau. But now what is the convolution really doing? Well, let's just take a particular value of t. Let's say we're looking at the value of 3. Let's say t equals 3 for this example. Then where does 3 appear? If I want to compute y of 3, where does it appear? Just right here, h of 3 minus tau. What does that look like? Well, h of 3 minus tau, look at where that t appears. It's right there. So that means that right edge must be at 3, and it's going to go back. So this is my t. I'm located at 3 right now, and it goes back to t minus 10. Okay, so this is my h of t minus tau function. And now what does the convolution ask us to do? The convolution asks us to multiply these two functions. How do you multiply two functions? Well, you just multiply them at every point. So you take this value, multiply it by that value, multiply it by that value, right? That value, multiply it by that value, and so on. Okay, you multiply these two functions and then you integrate. Multiply these two functions and then integrate. By the way, these rects have height 1/10. Okay, that's what it asks you to do. And so let's try and do that. Okay, how can I simplify this function? Well, h of t minus tau, right? H of t minus tau, it's almost always 0. It's almost always 0, right? The only times it's not 0 is between t minus 10 and t. So I might as well just integrate from t minus 10 to t, because otherwise this function's 0. And in that region, I get x of tau times what? Well, h of t minus tau is 1/10 there. Right, so I just multiplied those two functions. Now I can bring the 1/10 out, and I get this expression. Okay, and so we can see actually, what does this tell us? It tells us that this convolution, this is really getting to the heart of convolution. This is a specific example, but this is the point, and I'll explain it more in a second. This convolution, what does it produce? It produces a function, y of t, such that y of t, what does it equal? Well, let's think about it. What is this really saying? It's saying integrate x of t from the time t that we're at now back to 10 time units earlier. In other words, integrate x of t starting 10 time units ago up to the current time, and divide by 10, divide by the length of that interval. That's just computing the average value of x of t over the last 10 time units. Y of t equals the average value the average of x of t over the past 10 time units. So that's what convolving with this particular impulse response is doing. It's just producing a new signal where at any point in time, the value you get is the average of your input signal over the past 10 time units. And this is actually used in practice. Maybe some of you have heard this before if you've done any investing. This is used in practice in the stock market. Right? And people who study the stock market, and it's called a 10-day moving average. Maybe you've heard of this before. It's a 10-day moving average. Now there, maybe things are kind of in discrete time. You'll see more of that in 101, but this is the main idea. Okay, that what this convolution is doing is just at any point in time, it's giving you the average of the past 10 time units. Maybe they're days, maybe it's seconds, whatever. Okay, but that's what this convolution is doing. H of t convolved with x of t. In this case, based on this h of t function, is giving you the average of your x of t function over the past 10 time units. That's actually what this convolution is doing. And with that intuition, we can look back and say, all right, how could I have understood that from this picture? Well, let's think again about what the convolution is doing. All it's doing is integrating x of tau. We're going to integrate x of tau, but we're not just going to integrate x of tau. We're going to apply these weights. H of t minus tau is providing a weighting function, W-E-I-G-H-T, weighting function. Okay, so as we integrate x of t, we're going to apply the weights from this function, multiply them by this x of t, or sorry, x of tau at every value, and then integrate. So what's happening here is we're saying, all right, look at these values of x of tau and apply this weight to them and integrate them, add them up. And that's where the weighted average comes from in this case. We're going to multiply all those values by a tenth, right? That's what this weighting function is telling us. Multiply all those values by a tenth and integrate them. Multiply all the other values by 0. Don't worry about them. Okay, so that's what the convolution is doing. If you start with a function x of t, okay, and you convolve it with another function, what you do is you flip and you shift to get this function h of t minus tau, and then that function is just being used to weight all the values of x of t when we perform the integral. And I rigged this one up so that the result we got was actually the 10-day or 10 time unit weighted moving average of our function. Now, let's say you wanted the past 5 days to count more than the previous 5 days. So you want it to be more recent. The most recent 5 days count a certain amount. They have a certain weight. And the 5 days before that have less of a weight. You could just use a different impulse response that looks maybe something like this. This is 5 and this is 10. So now when you flip and shift that, what you get up here is something that looks like this, where now, and maybe we can change the heights if we want, but now we're weighting the past 5 days by a certain amount and adding that to weighting the 5 days before that by some other smaller amount and still zeroing out all the other values. We don't care. We just want the past 10 days. That's all we care about at any point in time. Okay, so you can see how this is a pretty general notion that can be used to achieve a lot of different results. Okay. Okay, so that's what convolution's doing. Okay, you're taking your x of tau and you're using this function as weights when you go to integrate this x of tau. Okay, so you're just kind of applying as you move this across at any time t. If you move this across for any time t, you're going to apply these weights and integrate. So right here, we take the weighted average of maybe the past 10 time units before time equals 10 in this case, right? You can move this across and just keep getting that weighted average in this case, applying the weights of this function to the function above and integrating. You might have also seen this maybe with COVID trackers, right? You have sort of the total cases, and then you have another graph that is sort of smoothed out and it tells you the average maybe over the past month. It's exactly what's happening here, just instead of t minus 10, maybe it's t minus 30 for a month, right? And that's an instance of convolution in the real world too. So you can express a lot of things in the real world as a convolution. This is just one example. It's used in neural networks. It's used in image processing. So if you go into image processing, when you get to blurring filters or edge detection filters, it's actually going to be, in this case, a two-dimensional convolution because it's on an image. but still a convolution. You take one function and you kind of move it across the other image, multiply and integrate. You're using the other function as weights to multiply by these values of x of tau, so that when you integrate it, you get a weighted integral. All right, so I think I've said enough about this. I've said things probably many times, but I really want it to sink in. Now that we sort of have a better idea of what convolution is really doing, okay, maybe I'll move this back over so it's kind of lined up with our example 3. Let's look at some actual examples here. Okay, so these are going to be some longer examples that take quite a bit of calculation, but it's good to see. And then at the end, I'll show you an animation kind of summarizing what we did, so you can see it all sort of animated. All right, so let's take a specific example now. Let's say we want to convolve this rect function. This is sort of the classic first convolution example. We want to convolve this square. Okay, we want to convolve it with this other square, the same one. Okay, so we're just convolving it with itself, but so that we don't get confused, I'm going to call this one h of t. So you can imagine x of t could be our input to an LTI system, h of t is our impulse response, and we want the output, so we want to convolve these. So I'll even write that. So if x of t is the input to an LTI system with impulse response h of t, then what is the output y of t? That's what we're going to answer now, because we know the output is the convolution, right? The output y of t, we proved this in a previous video, is x of t convolved with h of t, which is the integral of x of tau, h of t minus tau, d tau. Okay, so this is what we have to compute. So now let's do what we did above. Let's flip and shift, because we want to get our hands on both of these functions. Remember, x of tau is easy. We can just change t to tau in that picture. We need h of t minus tau. So we're going to flip and shift. So here, let's flip. Okay, how do I flip this function to get h of negative tau? Well, I just flip it across the vertical axis. That's easy enough. Okay, I like to label this as my t position, because in this example of h of t minus tau, t is just 0 here. So that 0 is playing the role of my t here. This was the flip stage. And now we need to shift. And how do we do that? Well, as we saw above, if I want to graph h of t minus tau, let's say that's my t value right there. Okay, these are all functions of tau. T is a constant here, right? In this integral, tau is the variable, t is some constant. Okay, of course, t can be anything, but in this integral, t is not a variable, it's just fixed. And then we're computing this integral for any value of t is really what we're doing. Okay, so h of t minus tau, how do I graph that? Well, I just take this t position, as I like to say, and put it on t, and then fill in everything else. So the function just is a square, and this left side is just 1 unit to the left of the t position, right? So t minus 1. All right, so that is h of t minus tau. So now we have both of these functions. Now we have to multiply them and integrate. You can imagine for different values of t, for different places where this square is located, okay, this integral might have different bounds, it might have different values, it might change depending on the value of t, depending on where I've shifted the square to be. So there are different cases we have to consider. Okay, so what I'm going to do is I'm going to draw my x of tau, okay, which we know is x of tau. Okay, that's this function. And now I'm going to shift h of t minus tau along this function and consider the different cases I get. Okay, so if I take, let me just draw it. T and t minus 1. Okay, this is tau. This is h of t minus tau. Okay, so we can consider some different cases. The first case could be over here, where there's no part of the tau axis where both of these functions are non-zero, like over here. When I multiply these two functions, as I do in the convolution, when I multiply them, at every tau value, at least one of these functions is 0. Over here, x of tau is 0. Over here, h of t minus tau is 0. So for every value of tau, when I multiply these functions, I'm just going to get 0 times something, which is 0. Okay, so that's kind of a first simple case when these squares kind of don't have any part of the tau axis on which they overlap. Okay, so I'll consider that as my first case. And when does that case occur? You can see it occurs all the way up until t. You can see in this picture I'm moving that t value hits 0. Okay, so this case occurs whenever t is less than 0. Okay, and now I'm going to draw these dotted lines because I'm going to draw the cases below, and we have to know where these important locations of 0 and 1 are. Okay, what could be the next case? Well, as I move this function across, I could consider the case where these two squares are kind of partially overlapped. Okay, because then the values that I'm integrating, okay, the places where they're both non-zero, are going to be, you can see, between 0 and t. So in this integral, when I multiply these two functions, okay, I want to see where are the places where I get something non-zero that I have to integrate. That means both of those functions have to be non-zero. We can see here that the intersection of where both of these functions are non-zero is right there between 0 and t. Okay, so that's going to be this case. And we'll use that observation I just made about the overlap when we actually go to compute the integral. And you can see that this case is true whenever this t variable is between these two lines, right? Then we're still partially overlapped with those two rectangles in that way. And so this is whenever t is between 0 and 1, right? T is between these lines. How about the next case? Well, what about when I'm kind of partially overlapped, but on the other side? Then I have t and t minus 1. Okay, I'm just moving this function slowly across. You can see here where the locations, where the values of tau where both functions are non-zero. We can see now it's from t minus 1 up to 1. So those bounds of that integral are different. Over here is between 0 and t. Now it's t minus 1 up to 1. Okay, and so that's going to be a different case we'll have to consider. And this case is true whenever this t minus 1 side is between 0 and 1. So if t minus 1 is between 0 and 1, you just add 1 everywhere, and you get that t is between 1 and 2. That's that case. And then finally, we have the final case when the square is completely shifted onto the other side. Okay, and then you can see there's no overlap where both these functions are non-zero. So again, just like the first case, for every tau value, at least one of these two functions is going to be 0. So the whole integral is just 0. The whole integral would just be 0 in that case. So this is going to be an easy case for us to consider too. This is whenever t minus 1 is to the right of this line. T minus 1 is greater than 1, which just means t is greater than 2. Okay, so these are our 4 cases where I can consider each one in turn. Okay, and I know this is kind of a long process, but as we see more examples and you try them on your own, you'll get the hang of it. Okay, but I'm going to consider these 4 cases, and let's just take each one by one. So let's look at case 1. This is when t is less than 0. And so we have that picture above. So we have y of t. It's going to be our convolution integral, x of tau, h of t minus tau, d tau. Okay, and what is this integral? Well, look, for every tau value you give me, at least one of these two functions is 0. Over here, x of tau is 0. Over here, h of t minus tau is 0. Okay, actually, both of them are 0 in that case. But the point is there's no tau value where both of these are non-zero, because it would be the intersection of these tau values and these, but you can see there's no overlap between those sections. Okay, so for every tau value, at least one of these functions is 0, so I'm just integrating 0, which gives me 0. So when t is less than 0, the convolution of these two functions is 0. Now I'll just make a note. This is because no values of tau. There are no values of tau where x of tau doesn't equal 0 and h of t minus tau doesn't equal 0. Okay, and so that integrand is just always 0 for all tau, and the integral of 0 is 0. Okay, let's look at case 2. This is when t is between 0 and 1, right? And then let's look at our function again, y of t. Okay, we have x of tau, h of t minus tau, d tau. Okay, what's happening in this case? Well, in this case, we do have values of tau where both functions are non-zero, and they're right there. Right, they're right there. So you can see how helpful the pictures are. Okay, you could do this whole process algebraically, and we'll see more examples of that as we go on. I think pictures are important for now, where you actually get, explicit expressions for these two functions, and you kind of manipulate things algebraically. And like I said, we'll see examples of that as well. But I think pictures are way easier because it allows us to get these integrals very quickly. Okay, so we're in the second case, and I want to integrate x of tau times h of t minus tau. Okay, so I want to find all the tau values where both of these functions are non-zero, because if either function is zero, I don't have to integrate there. You can see that the only locations where they're both non-zero are right there. And you can see that's when tau is between 0 and t, right? I have to start at 0 because of this function and go up to t because of that function. So I start at 0 because of x, and I go up to t because of h of t minus tau. And the only values of tau where both functions are non-zero, where I get something non-zero in this integral, are when tau is between 0 and t. So I can change that, the integral bounds, to be between 0 and t. Otherwise, you're just integrating 0, which is 0. Okay, now what are the values of these functions in that region? Between 0 and t, what does x of tau equal? It just equals 1. Times, what does h of t minus tau equal? It also just equals 1, right? That's square at height 1. Maybe I'll label this one. They all have height 1, so I have 1 times 1 d tau. And that's just the integral of 1 from 0 to t. That's just t. So the convolution of these two functions when t is between 0 and 1 is just t. Let's go on to case 3. This is when t is between 1 and 2. Okay, do the same thing. X of tau, h of t minus tau, d tau. Now we're in this case 3, and where should we integrate? Where are the values of tau where both these functions are non-zero? Well, you can see tau has to be at least t minus 1, because this function is 0 to the left of that. And it can be at most 1, because x of tau is 0 to the right of that. So I have to be somewhere in here, right? Between t minus 1 and 1. Okay, so I want to integrate from t minus 1 up to 1. And again, what are the values of our functions in those regions? We can see the same as before, they're both 1. So I get 1 times 1 d tau. And this is just going to be integrating this function 1 from those bounds. So I get 1 minus t minus 1, okay, which is just 2 minus t. Okay, so you can see at every point we get a function of t as our convolution, which we should, because we know the convolution is a function of t. We shouldn't have any taus left over. That's the integration variable. So if you end up with some taus in the end, you know something went wrong. All right, finally, case 4. This one should be pretty easy. And this was when t was greater than 2. Okay, I'll write it out one more time. Y of t is this convolution. X of tau, h of t minus tau d tau. But again, all of the tau values have at least one of these two functions equal to 0, right? There's no overlap between the tau values where both of these functions are non-zero. Okay, so for every tau value, at least one of these is 0. And so for every tau value, this product is always 0. So we just get 0. Okay, and I'm going to copy the same justification. There are no values of tau where both of those functions are non-zero, so their product is 0 for all tau. You can see it visually up above pretty easily. Okay, so that's all the cases. So we actually found our convolution now. So y of t, which is the convolution of x of t and the impulse response h of t, what is it? Well, we found all the cases. So we're either going to get t, 2 minus t, or 0. Okay, so I'm going to list those options. We're going to get t, 2 minus t, or 0. We get t whenever t is between 0 and 1. 2 minus t whenever t is between 1 and 2. And 0 else, otherwise. All right, so what does this look like? What does the convolution of those two squares actually look like? We can pretty easily plot this function. And it just looks like this. Between 0 and 1, I just get the function t. And between 1 and 2, I get the function 2 minus t. So that's a line with slope 1. Okay, and you can see when I plug in 1, I get 2 minus 1, which is 1. So it goes through that point 1, 1, and it has slope, or sorry, I guess that's slope 1. Slope negative 1. So it goes down to make the other side of this triangle. Okay, so that's it. That's our y of t, and it's 0 everywhere else. So that's what you get with the convolution of two squares. And it was a long example, but I wanted to go slowly and methodically so we understood everything. Now let me quickly share a Desmos file I made that animates this. Okay, let me find it right here. Okay, so here's a Desmos file. What's going on? What's going on is I have two rect functions, okay? One of them is blue, that's this one, and one of them is green. And as we saw in our problem, they were both the same. That's why they're overlapped. They both just have height 1 between 0 and 1. And we want to try and compute the convolution of these two functions, the red and the green. So what do? We take the second one, the green one. We're going to flip it. There we go. I flipped it across the y-axis. Now it's this red flipped rectangle. And now we're going to shift it for any t value. So we're going to shift it along. You can see, like, for instance, right here, t is -1. And sure enough, that right edge, that t position, was at -1. And the left edge is 1 unit to the left. We're going to shift this across. And as we shift it, this black line with this black dot right there is going to be plotting the convolution. So as we saw, when the red rectangle was to the left of the blue and all the work we just did, the convolution was 0, right? Because there's no values on this axis where both of these functions are non-zero. There's no overlap. But now, right when I get up to 0 and start going by it, now we get some overlap. Okay, and the purple is showing you the function that is the product of these two functions. So in this region, 1 times 1 just gives me 1, and then the purple is showing you the integral of that product. That's what the convolution does. It integrates the product of these two functions. So the purple is that integral, okay, which you can see. What is the area of this purple? It's 0.3 times 1. That's 0.3. You can see this convolution is 0.3 right there. Okay, so this convolution line is plotting the area of the purple as I move it across. And you can see this was the left half of the triangle until they're perfectly overlapped. Okay, then when I multiply them, I get the function 1 integrated from 0 to 1, gives me 1. The area of the purple is 1. And sure enough, the value of my convolution is 1 there. And then as I start to leave, the overlap is decreasing. The purple area is decreasing until we get the right side of the triangle. Okay, and that black line is exactly what we got. And we did it exactly in this way. We just thought of all the cases of this rect moving across this other one, this square moving across the other one. Okay, and that is what the convolution does. Now, with this Desmos file, we can actually manipulate these a little more. I have these controls. We could see what happens if I make my second rect twice as wide, maybe. Okay, then we still flip it. We get this function. Okay, I'll put it at t equals 0. We flip it. We get the red function. Now I can forget about the original green, and I'm going to start shifting this over. And the first part's going to be the same, right? This overlap is the same as we saw before. But now, as I keep moving it, right, the product of these two functions still gives me this purple line here at 1, and so the area stays at 1. And so you can see the convolution stays constant until later on, as we exit, we get that other side that was of a triangle. Now it's the other side of a trapezoid. Okay, so this is what the convolution is doing. And of course, we can manipulate them more if we wanted. Right? What happens if I increase the height? Maybe let's double the height as well. Now I flip and shift. And now you can see the product of these two functions is 1 times 2, which gives me the value of 2 for this purple line. And so the purple area now is getting larger faster. And so you can see that the slope of this line is higher, right? It's increasing more quickly. This area is larger. It's increasing all the way up to 2 as it goes to the right by 1. And then as we move, we still have that constant height value because this overlap area is not changing. And then we go down. Okay, so that would be the convolution in this case of these two functions. Okay, so hopefully this gives you sort of an animated picture of what we just did by hand. All right, let's go back. All right, we're back, and I have one more example I want to do. I'll start a new page. Okay, so let's actually, there's enough room. I'll just start here. Let's look at two different functions now, and they're going to both be these decreasing exponential functions. Okay, so they're going to start at 1. This is going to be x of t, which is going to be e to the negative at times the unit step function. And what's my impulse response going to be? Well, it's going to be similar. It's going to be e to the negative bt. So I'll allow for a different scaling in the exponent, but still it's going to be something that looks somewhat like this. Okay, and so we're going to suppose a and b are both positive. And for now, we'll just consider the case where a does not equal b. It's going to be very similar to the a equals b case, but I'll just say for practice, you can try a equals b case on your own. Okay. And we want to compute what we've been talking about. We want to compute y of t, which is going to be the convolution of x and h, which we know is this integral, x of tau, h of t minus tau, d tau. And so if x was an input to an LTI system with impulse response h of t, y of t is going to be our output. So this is what we're going to compute. How do we do it? Well, we're going to flip and shift. So let's flip first. Okay, this is going to be h of negative tau, which is h of 0 minus tau. Okay, so we flip it across the vertical axis, and we get this. Just flip this across the vertical axis. At 0, I like to label this as my t position. So I know this is the flip. But I know when I shift, as we saw before, and this is in terms of tau, by the way, if this was my t, I just want to put this t position, shift it so that that is located at t. That's a little too much. All right, so this is my h of t minus tau. That's my shifted version of my flip signal. All right, and now we're going to do the same thing. Now, let's look at the cases to consider. Okay, so I'm going to draw my function up here. This is my x of tau. There's this exponential function, decaying exponential. And now I'm going to take my shifted version, just like I did before. A shifted version, h of t minus tau. Okay. And here's my first case. This is, again, when t is less than 0. You can see we have no places on the tau axis where both of these functions are non-zero. That's kind of a typical standard first case. Comes up a lot. This is when t is less than 0. We can already tell the convolution in that region should be 0, right? Because there's no place on the tau axis where both these functions are non-zero. So in this integral, I'm just going to get 0 there. So that's going to be my case 1. And what's case 2? Well, should be probably pretty clear. It's if t is on the other side. Right? This is when t is greater than 0. And these are our two cases. There's nothing else to consider. There's no other way I could overlap these functions. Okay, so now let's take each case in turn, just like before. So case 1, this is when t is less than 0. My convolution, y of t. It's going to be this integral, x of tau, h of t minus tau, d tau. Okay, and we already said, look, again, just like before, there are no tau values where both these functions are non-zero, because here are the tau values where that function is non-zero. Here are the tau values where that function is non-zero. There's no overlap. They don't overlap anywhere. Okay, so that product in here is just always 0. Okay, I'm even going to copy the justification from before. Okay, so there are no values of tau where they're both non-zero, so the product's 0 for all t, so that integral is just 0. All right, now case 2, this is the more interesting one. Okay, what happens here? Well, we're going to get y of t. It's going to be this integral, x of tau, h of t minus tau, d tau. And we can see that we know that where are we going to want to integrate? Where are the tau values where both those functions are non-zero? So where are the tau values where that product is non-zero, which we should be integrating? We can see they overlap right here. It's whenever tau is between 0 from this function and t. from that function. That's the only place that both these functions are non-zero. So we already know this integral should eventually go from 0 to t. But now I'm going to show you that other algebraic way that's sometimes useful for finding the bounds of an integral, maybe without drawing a picture, although I do think you should draw pictures. I think it's more useful. You can get the answer more quickly in a lot of cases. So let's actually plug in. What is x of tau? I know what the function is. I'll just plug in tau everywhere there. Yeah, so I get e to the negative a tau times u of tau. And what is h of t minus tau? Well, again, I know what that function is. I'll just plug in t minus tau everywhere. Okay, so I'll get e to the negative b times quantity t minus tau, and then plug t minus tau in for the unit step as well. This is times e to the negative b t minus tau times u of t minus tau d tau. Okay, now how can we simplify this integral? Well, look at these two unit steps. Unit step functions are sort of like switches. They're either on or off. And we want to know where they're both on. Because if they're off, they equal 0. And so this integral would just be 0. We want to know where they're both on. Okay, so this one is on when, well, remember what the unit step looks like, right? It's on when it's off when the argument's less than 0, on when the argument is greater than 0. So this is on if tau is greater than 0, and this one is on if t minus tau is greater than 0, which just means t is greater than tau. And we want them both to be on because if either is off, then it's going to equal 0, which is going to zero out this whole integrand, so we don't have to integrate there. We want where they're both on, and so we can see we need tau to be greater than 0. We also need tau to be less than t. There you go. That's our 0 to t bounds that we got just by looking at the picture. The overlap is between 0 and t. That's where they're both non-zero. Okay, so either way, you can get the correct bounds, and what we're left with is the functions e to the negative a tau, e to the negative b t minus tau d tau, right? Because when they're on, both these functions just equal 1, or I don't have to write times 1. Okay. Now what can I do? Well, I have an e to the negative bt that doesn't depend on tau, so I can bring it out. We just have to solve this integral at this point. Kind of the hard work is over. And now I have e to the what? Well, I have negative b times negative 1, which is b, and then minus a, all times tau. We can do this integral. We have negative e to the negative bt times 1 over b minus a, e to the b minus a times tau, from 0 to t. And here's where I'm going to use that b does not equal a. So if you're doing the b equals a case on your own, this is where things would change, right? Because you can't divide by 0. So to take this step, I need b not equal to a. You can think about what would change if b equals a here. Okay. And now I'll just plug in for those limits. So I get 1 over b minus a times what? E to the b minus a times t, minus what I get when I plug in 0, which is just e to the 0, which is 1. Okay, and now I can multiply this thing, e to the negative bt, through both these terms, and it cancels the e to the bt here, so I'm just left with e to the negative at, and then minus e to the negative bt, what I multiplied through, all divided by b minus a. Okay, so there we go. We've done it. We found out what the convolution is in both of these cases. Okay. And when t equals 0, it doesn't really matter. Like I said, with these unit step functions, we're not going to worry about right at that location when they change. It really doesn't matter. It could be whatever you want. So often we don't care about that one particular point. We care about the function in general. Okay. So now, finally, our y of t going to be what? Well, it's either e to the negative at minus e to the negative bt over b minus a. And that was when? That was if t is greater than 0. Okay. And otherwise, what do we get? We just got 0. We just got 0. Okay, so there it is. We computed that convolution. Okay, and these do take a lot of work. But hopefully as you start to understand how they go and you get practice, you'll be able to get a little bit faster at it and understand it more as we go through the class. So just real quick, I want to do the same thing and show you the Desmos file for this case. So let me share that. Where is it? Right there. Okay, so this is what we were looking at before, but I have this other one rigged up. Okay, so I have these two exponentials. One is in blue, one is in green, and I can adjust, their decay factor. This was the A and the B, right? This was the A and the B we were talking about. So I'll just pick random ones, 1.5 and 0.5, say. Okay, and what do? We want to take, in this case, the green one, the second one, we want to flip it. That was our flip version, h of negative tau. Okay, now we don't need the green one anymore. Now we want to shift it. I want to shift it for all different values of t. So you can see right here, when t is -1, this right side is right at -1. That was our t position. You can see as I start to move it across, look at what happens. Right now, this region is where both functions are non-zero. This purple line is their product, right? We multiplied them. And then the purple area is the integral, and that area is the value of this convolution right there, that black dot. Okay. So for instance, you can see this purple area, this square is a half times a half, that's a quarter plus a little bit. You can see the value here is a little more than a quarter. Okay, so this value is just plotting the area under the product of these two functions. And as we keep going, you can see the function that gets graphed, it looks like that. And it turns out that is exactly the function that we obtained before. Okay, doing it by hand. And of course, now we can do a similar thing. I have these controls. We can say what happens if I make my original green function maybe twice as big. Okay, and what's going to happen is we're just going to get the same thing, but multiply by 2. It's kind of twice as big now. It's that same sort of graph, just twice as large, because the area now has just doubled at every point. Okay? Remember, the area before was like 0.30 something. Now it's 0.613. It's exactly double what it was before. Okay, and of course you could, do other things to these exponential functions. You could maybe time shift it a little bit. Then what happens? Well, now let's see that, the functions still have not overlapped yet. So this convolution is still 0. And now they start to overlap, and now the convolution starts to occur because now we have area to integrate. Okay, so anyway, this is what's happening sort of visually with the convolution. I'll put it back how it was. And this is exactly what we just did. By hand, this is just the animated version. Okay, so hopefully this kind of helps you understand the process of performing the convolution some more. All right, so that's all I had for this video, and I will see you in the next one.